Autonomics, a new frontier in intelligence. What if intelligence wasn't just about thinking, but about adapting, evolving, and self-regulating? Imagine a world where machines don't just follow commands, but make decisions, learn from their surroundings, and protect themselves. A world driven by autonomics. But what exactly is autonomics? The word autonomics actually comes from autonomous, a term that traces its roots to the Greek word autonomos. It means self-governing or self-ruling. When we talk about autonomics, we're not just talking about machines that follow routines. We're talking about systems that can think for themselves, adapt on the fly, and regulate their own functions. It all started with the fundamental ideas of cybernetics and control theory, concepts that go back to the 20th century, when pioneers like Norbert Wiener imagined machines that could self-regulate through feedback loops. But it wasn't until the explosion of machine learning and neural networks that we finally saw machines not just performing tasks, but learning, evolving, and adapting. Today, autonomics is everywhere. In healthcare, machines monitor patients and adjust treatments in real time. In manufacturing, robots detect wear and tear and fix themselves before a breakdown happens. In finance, algorithms continuously analyze market trends and make decisions faster than any human ever could. And in our smart cities, energy grids adjust power flows to balance supply and demand, all without human intervention. Autonomics is not just technology. It's a new frontier in intelligence, one where machines don't just work for us, they think with us. But with this power comes a challenge. Can we truly trust systems that act on their own? Are we ready to share our world with machines that make decisions without us? As we step into this new era, autonomics will redefine how we think about intelligence. It's not just about creating smarter machines. It's about reimagining the relationship between humans and technology. Welcome to the new frontier of intelligence, where machines learn, adapt, and evolve in ways we never thought possible. The engine of autonomy. At the heart of autonomics lies a complex yet elegant system architecture designed to empower machines with the ability to think, adapt, and make decisions on their own. These systems are not merely automated, they are autonomous, capable of functioning independently without constant human intervention. The distinction between automation and autonomy is critical, as the former follows predefined instructions, while the latter adapts and learns from real-time data and changing environments. The engine of autonomy is not a single component, but an integrated framework of advanced technologies, algorithms, and control mechanisms working in unison. From machine learning models to real-time data processing, each layer contributes to an overarching goal: to create a self-governing system that can sense, analyze, decide, and act. This chapter will explore the fundamental building blocks of the autonomic engine and examine how these systems evolve, learn, and adapt to complex scenarios. The core components of the autonomic engine. To truly understand the engine of autonomy, it is essential to break it down into its fundamental components. These include perception layer. The perception layer acts as the sensory gateway, gathering data from the environment through various sensors and inputs, whether it's capturing temperature changes, visual data from cameras, or sound from microphones. This layer continuously feeds raw data into the system. Data processing layer. Once collected, the data passes through the data processing layer, where it is cleaned, organized, and structured for analysis. This is where edge computing and real-time analytics come into play, allowing the system to process vast amounts of information with minimal latency. Decision-making layer. The decision-making layer is where the core of autonomy resides. Using artificial intelligence and machine learning algorithms, the system analyzes the processed data, identifies patterns, and makes decisions based on predefined logic or adaptive learning models. This layer also includes predictive analytics, enabling the system to forecast outcomes and optimize responses accordingly. Action layer. After decision making, the action layer executes the chosen course of action. This might involve controlling mechanical systems, sending commands to other devices, or generating reports for human oversight. The feedback loop then captures the outcomes to refine future responses. Machine learning, the brain of autonomy. At the core of the autonomic engine lies machine learning, ML, the primary driver of decision-making and adaptive responses. ML algorithms allow systems to learn from data, predict future events, and adapt to changing conditions. There are several key techniques used in autonomic systems. Supervised learning, algorithms trained with labeled data to make accurate predictions or classifications. Unsupervised learning, identifying patterns or correlations in data sets without predefined labels. Reinforcement learning, learning by trial and error, where the system optimizes actions based on rewards and penalties. Deep learning, utilizing neural networks to process and interpret complex, high-dimensional data. These methods combine to create systems capable of intelligent decision-making, self-improvement, and continuous learning without needing constant human guidance. Adaptive algorithms and feedback loops. One of the most profound aspects of the autonomic engine is its ability to adapt and evolve. This capability arises from the use of adaptive algorithms integrated with feedback loops. Here's how it works. Real-time monitoring, continuously observing system performance and environmental variables. Data feedback, capturing results and analyzing deviations or unexpected behaviors. Algorithm adjustment, modifying the underlying models or decision criteria based on new data. Implementation, reconfiguring the system to align with the refined parameters. The presence of feedback loops ensures that the autonomic engine is not static. Instead, it dynamically responds to changes, continuously improving its efficiency and reliability. Autonomic frameworks and architectures. Creating an efficient autonomic engine requires a robust framework, one that blends hardware, software, and algorithmic intelligence seamlessly. Several architectures have emerged to support such systems, including decentralized networks, reducing single points of failure by distributing decision-making across multiple nodes, service-oriented architectures, SOA, modular designs that allow components to communicate through standardized interfaces, event-driven architectures, triggering responses based on specific data patterns or anomalies, cloud and edge integration, balancing centralized processing with local, real-time analytics. A well-constructed autonomic framework not only ensures resilience, but also fosters scalability, allowing the system to grow and evolve without significant structural changes. Challenges and considerations. Despite its potential, building a reliable autonomic engine presents several challenges. Data integrity, ensuring the accuracy and quality of the data being processed. Security concerns, protecting the system from cyber attacks that could manipulate decision-making processes. Computational efficiency, balancing high-speed processing with energy conservation. Ethical implications, determining the level of human oversight needed to mitigate risks. Overcoming these challenges requires a multidisciplinary approach, incorporating elements from computer science, cybersecurity, engineering, and ethics. The road ahead, enhancing the autonomic engine. Looking ahead, the engine of autonomy will continue to evolve, with advancements in quantum computing, neural network optimization, and bio-inspired algorithms. These developments will push the boundaries of self-learning systems, enabling them to tackle more complex problems with unprecedented efficiency. As we continue to integrate autonomic engines into critical infrastructure and daily life, we must balance innovation with responsibility, ensuring that autonomous systems serve humanity rather than outpace it. The engine of autonomy is not just a technological marvel. It is the foundation of the intelligent future. The blueprint of self-governance, foundational principles. Autonomics is more than just technology. It is an ideological leap forward in how machines interact with their environments and manage themselves. At its core lies a set of foundational principles that define not just what autonomic systems do, but how they think, respond, and evolve. These principles form the blueprint of self-governance, guiding autonomous systems to function independently while remaining resilient and adaptive. To fully grasp the potential of autonomics, it is essential to understand the philosophical roots and foundational ideas that underpin self-governance. This chapter explores the conceptual framework of autonomy, tracing its evolution from human self-governance to machine intelligence. We will delve into how these guiding principles have shaped modern autonomic systems and continue to influence the design and functionality of intelligent technologies. The philosophical roots of autonomy. The concept of autonomy predates modern technology by centuries, rooted in philosophical discussions on self-governance and free will. In the context of human society, autonomy signifies the ability of an individual or a community to govern itself without external control. This notion of self-determination laid the groundwork for later interpretations in both political theory and technology. In philosophy, thinkers such as Immanuel Kant argued that autonomy is fundamental to moral agency. Humans must be able to make rational choices independently. This idea resonates with how we envision autonomous systems today, machines that make decisions without human intervention, driven by internal logic and adaptive reasoning. The transition from human autonomy to machine autonomy required reimagining these principles through the lens of technological advancement. Instead of moral reasoning, machines must exhibit operational reasoning, where decision-making, adaptation, and self-management become integral to their function. The evolution of self-governance in technology. As technology evolved from simple automation to complex autonomy, the concept of self-governance adapted as well. Initially, machines could only perform static, pre-programmed tasks. With the advent of cybernetics and control theory, systems began to incorporate feedback loops, allowing for basic self-regulation. However, true self-governance remained elusive until the emergence of artificial intelligence and machine learning. Key milestones in technological autonomy. Cybernetics, 1940s, 1950s. Introduced feedback loops for basic regulation. Artificial intelligence, 1950s, 1970s. Focused on symbolic reasoning and rule-based systems. Machine learning, 1980s, 2000s. Enabled pattern. Recognition and adaptive learning. Deep learning and neural networks, 2010s present. Revolutionized decision-making and contextual understanding. Each of these stages contributed to the foundational principles of autonomics, evolving from simple command execution to complex, self-governing systems capable of reasoning and adaptation. The core tenets of self-governance. The essence of autonomics is rooted in four fundamental tenets that guide autonomous systems. Self-determination. Systems must define their own operational boundaries and make decisions independently. Self-regulation. The ability to monitor and adjust performance without external interference. self-adaptation, continuously evolving in response to new data and conditions, self-preservation, maintaining stability and security even under adverse conditions, guiding frameworks of self-governance. To translate these philosophical principles into practical applications, developers use guiding frameworks that align with the inherent logic of autonomy. Rational decision frameworks establish rules for decision-making based on cost, benefit, and risk analysis. Adaptive learning models employ machine learning algorithms to update internal logic as conditions change. Dynamic response protocols maintain situational awareness and implement real-time responses. Ethical and safety guidelines incorporate principles of responsibility and accountability to mitigate risks. The human element in machine autonomy. While the goal of Autonomics is independence from human oversight, it is crucial to maintain a human-centric perspective. In designing autonomous systems, it is vital to ask how much autonomy is too much. What level of human oversight is necessary to ensure safety? Should machines ever make decisions that impact human lives without input? By incorporating ethical considerations and transparency, engineers and developers can create systems that respect human values while maximizing operational efficiency. Challenges in establishing self-governance. Despite the clear blueprint, implementing self-governance in practice faces numerous challenges. Complexity in decision-making. Machines must not only make decisions, but also justify and explain those decisions when needed. Bias and fairness. Machine learning models must be trained to avoid biases that could skew decision-making. Adaptive safety protocols. Autonomous systems must balance freedom with safety, ensuring that self-governance does not compromise security. Societal impact. As autonomous systems become more prevalent, their influence on labor markets, privacy, and ethics will intensify. These challenges highlight the need for responsible innovation, designing systems that balance freedom of operation with accountability and oversight. The blueprint for the future. The future of autonomous systems lies in harnessing the principles of self-governance, while maintaining human-centric control and oversight. As we continue to develop more sophisticated and intelligent technologies, it is essential to keep philosophical considerations at the forefront, ensuring that autonomy serves humanity rather than replacing it. By adhering to the foundational principles of self-determination, self-regulation, self-adaptation, and self-preservation, we can build a new generation of intelligent systems that not only perform tasks autonomously, but do so with a sense of responsibility and purpose. The ultimate goal is to create machines that not only think independently, but also align with human values and ethics. Pillars of Autonomics. Structure, coherence, standardization. As autonomous systems evolve, their effectiveness hinges not only on their ability to self-govern, but also on their capacity to maintain structure, coherence, and standardization. These three pillars are crucial for creating intelligent systems that operate reliably, consistently, and predictably across diverse applications. Whether in industrial automation, healthcare, or smart cities, these foundational elements ensure that autonomic systems can seamlessly integrate, scale, and communicate within complex environments. While previous chapters explored the philosophical and foundational principles of autonomy, this chapter delves into the practical framework that transforms conceptual autonomy into actionable, real-world implementations. The pillars of Autonomics serve as guiding structures that maintain order and coherence amid the inherent complexity of autonomous technologies. The three pillars of Autonomics. The pillars of Autonomics are interdependent principles that shape the reliability, scalability, and interoperability of self-governing systems. These pillars are structure. creating organized, modular systems with clear hierarchies and relationships. Coherence, ensuring consistent behavior and decision-making within and across systems. Standardization, establishing common protocols and frameworks for communication and integration. Together, these pillars form a comprehensive approach that makes Autonomics robust, consistent, and adaptable, whether applied to machine learning frameworks, industrial automation, or AI-driven infrastructure. Pillar 1, structure, the framework of autonomy. The first pillar, structure, represents the architectural framework that supports Autonomics. An autonomic system without structure is prone to fragmentation and inefficiency. Therefore, creating a clear, modular architecture is essential for maintaining functional integrity and adaptability. Key components of structure. Modularity. Systems are divided into independent, self-contained units that can be developed and maintained separately. Hierarchical organization. Establishing layers of control and decision-making to avoid bottlenecks and maintain flexibility. Redundancy and fault tolerance, including backup modules and pathways to ensure continuity in case of failure. Layered architecture, separating data processing, decision-making, and action layers to maintain clarity and efficiency. Benefits of structured systems. Scalability, easily integrate new components or expand existing capabilities. Maintainability, simplifies troubleshooting and upgrades. Resilience, reduces the risk of system-wide failures by isolating faults. Interoperability, allows seamless communication between components through standardized interfaces. Pillar 2, coherence, consistent behavior and decision-making. The second pillar, coherence, addresses the challenge of maintaining consistency across a network of autonomous systems. Whether distributed across a city or within a single facility, autonomous components must act cohesively, aligning their behaviors to avoid conflicts or redundancies. Elements of coherence, unified decision logic, ensuring that all components operate under consistent decision-making frameworks. Adaptive synchronization, harmonizing real-time responses and updates to maintain system stability. Context, awareness, utilizing contextual data to ensure that decisions are relevant and appropriate. Integrated feedback, loops, continuously evaluating performance and adjusting strategies based on shared data and insights. Achieving coherence through communication. The primary mechanism for achieving coherence is robust communication protocols that enable real-time data exchange. Examples include distributed ledgers, ensuring transparent and synchronized data among autonomous entities. Decentralized control systems, allowing local decision-making while adhering to global objectives. Consensus algorithms, implementing methods like Raft or Paxos to maintain agreement across distributed networks. Pillar 3, standardization, unifying protocols and interfaces. The third pillar, standardization, is essential for achieving interoperability and consistency across diverse systems. As autonomous technologies proliferate, the lack of common standards can lead to fragmentation and inefficiency. Therefore, creating universal standards that define communication protocols, data formats, and control structures is vital. Principles of standardization. Uniform protocols. Establishing common communication and data exchange protocols to enable seamless integration. Interoperability standards. Designing systems to interface smoothly with legacy technologies and new innovations. Compliance with regulations, adhering to international standards and guidelines for data handling and security. Version control and updates, implementing consistent upgrade mechanisms to maintain compatibility across system versions. Standardization in practice. Standardization efforts are evident in several key areas. Industry 4.0 initiatives, creating interconnected manufacturing systems with standardized data protocols, smart city frameworks, harmonizing autonomous traffic systems, utility grids, and public services, cybersecurity standards, implementing consistent measures to safeguard autonomous systems from threats, integrating the pillars, a unified approach. Integrating structure, coherence, and standardization requires a holistic design philosophy that treats each pillar not as an isolated element, but as part of an interconnected ecosystem. Successful implementation relies on modular and scalable architectures, ensuring structural integrity while accommodating growth. Cross-system coherence, establishing clear communication pathways to synchronize actions. Adherence to standards, maintaining compatibility and predictability across all components. Case study, autonomous industrial robots. In a modern manufacturing facility, industrial robots must coordinate tasks like assembly, inspection, and material handling. Structured framework, modular robots with clear roles and responsibilities. Coherence protocols, real-time synchronization to avoid collisions and ensure task continuity. Standardized communication using OPC UA, Open Platform Communications, unified architecture for consistent data exchange. By implementing all three pillars, these robotic systems achieve high efficiency, resilience, and scalability, demonstrating the power of integrated autonomic principles. Challenges and future directions. Despite their importance, implementing the three pillars presents challenges such as complexity in design. Balancing modularity with coherence can increase system complexity. Evolving standards. Keeping pace with rapid technological advancements requires adaptive standardization. Cross-domain integration. Ensuring compatibility when integrating different technologies and platforms. To address these challenges, future research should focus on developing dynamic standardization, protocols, allowing standards to evolve alongside technological advancements, enhancing real-time coherence models, improving predictive algorithms and synchronization mechanisms, refining structural integrity, building more flexible and resilient architectures that can withstand disruptions. Conclusion: the pillars of autonomics, structure, coherence, and standardization, serve as the foundation for creating resilient, adaptable, and reliable autonomous systems. They enable not only self-governance, but also sustainable integration within complex technological ecosystems. By adhering to these pillars, autonomic systems can seamlessly transition from theoretical constructs to practical implementations, shaping the future of intelligent technologies. In the next chapter, we will explore real-world applications and case studies where these foundational principles are actively shaping modern industries, from smart manufacturing to intelligent transportation systems. Autonomics in action, a cross-disciplinary perspective. Autonomics, as a field, transcends traditional boundaries, merging artificial intelligence, machine learning, robotics, cybernetics, data science, and human-centered design. It is not confined to a single industry or application, but has the potential to revolutionize multiple domains. From healthcare to manufacturing, energy to transportation, autonomic systems are transforming how we approach productivity, efficiency, and decision-making. In this chapter, we will take a cross-disciplinary perspective on autonomics, examining how foundational principles and the pillars of structure, coherence, and standardization are applied in various industries. We will also explore the real-world challenges and opportunities that arise when implementing these systems, highlighting how synergistic integration across disciplines enhances performance and innovation. The role of autonomics in diverse fields. Autonomics plays a critical role in shaping the future of numerous industries, each with unique challenges and requirements. By leveraging autonomic principles, Organizations can enhance adaptability, optimize processes, and ensure resilience in a world where real-time data-driven decisions are crucial. Healthcare, autonomous diagnostics, and treatment. In healthcare, autonomic systems are deployed to enhance patient care and optimize clinical workflows. The integration of machine learning models, robotic surgery, and automated diagnostics has significantly improved precision and efficiency. Key applications: autonomous diagnostics, systems that analyze medical images to detect anomalies, such as tumors or fractures without human intervention. Robotic surgery, AI-driven robots performing minimally invasive procedures with enhanced precision and stability. Patient monitoring, continuously collecting and analyzing vital signs to predict health deteriorations. Medication management, automating prescription fulfillment and dosage monitoring. Challenges and considerations: ethical issues, balancing human oversight with machine autonomy in critical care. Data privacy, protecting patient data from breaches while maintaining system connectivity. Accuracy and accountability, ensuring diagnostic accuracy and defining liability in case of errors. Manufacturing, autonomous production and quality control. Manufacturing industries are increasingly adopting autonomic systems to enhance production efficiency, quality assurance, and resource management. The concept of Industry 4.0 heavily relies on the integration of autonomous robots, predictive maintenance, and smart factories. Key applications: smart assembly lines, self-configuring robots that adapt to product variations and dynamically optimize assembly processes. Predictive maintenance, using sensor data and analytics to predict equipment failures before they occur. Automated quality control, utilizing computer vision and deep learning to detect defects in real time. Supply chain optimization, autonomously managing inventory and logistics to reduce costs and downtime. Challenges and considerations: system integration, ensuring seamless communication between legacy systems and new technologies. Worker safety, balancing human-robot interaction to minimize risks. Operational stability, maintaining coherence and efficiency in high-demand environments. Energy and utilities, autonomous grid management. The energy sector is embracing autonomic solutions to manage smart grids, power generation, and distribution. These systems must self-regulate and adapt to varying demands and unexpected disruptions while ensuring reliable and sustainable energy delivery. Key applications: smart grid autonomy, managing power distribution by balancing loads and integrating renewable energy sources. Energy optimization, real-time demand forecasting, and automated energy routing. Failure recovery, autonomous rerouting of power in case of outages or malfunctions. Renewable integration, automatically adjusting to variable outputs from wind and solar sources. Challenges and considerations: cybersecurity, protecting critical infrastructure from malicious attacks. Data interoperability, maintaining standardization across different grid systems. Real-time decision-making, ensuring fast adaptive responses to fluctuations in energy supply and demand. Transportation, autonomous vehicles, and traffic management. Autonomic systems are revolutionizing transportation by enabling autonomous vehicles, real-time traffic management, and intelligent public transit systems. By leveraging machine learning and sensor fusion, these systems make transportation safer, faster, and more efficient. Key applications: autonomous driving, vehicles capable of self-navigation, obstacle avoidance, and adaptive route planning. Traffic flow optimization, using real-time data to synchronize traffic lights and reduce congestion. Predictive maintenance for fleets, monitoring vehicle health and scheduling maintenance proactively. Passenger experience, enhancement automating ticketing, route optimization, and real-time notifications. Challenges and considerations. Safety protocols, ensuring fail-safe operations in unpredictable environments. Regulatory compliance, navigating legal frameworks and safety standards. Data accuracy, maintaining precise environmental awareness to avoid accidents. Finance, autonomous trading and risk management. In finance, autonomics are used to analyze market trends, execute trades, and manage risks with minimal human intervention. By incorporating algorithmic trading and autonomous risk assessment, financial institutions can make decisions faster and more accurately than ever before. Key applications: algorithmic trading, autonomously executing trades based on real-time market data and predictive analytics. Fraud detection, using anomaly detection algorithms to spot suspicious transactions. Portfolio management, continuously balancing asset allocations to optimize returns. Credit scoring, automating risk assessment with data-driven decision models. Challenges and considerations. Market volatility, adjusting algorithms to respond robustly to sudden changes. Ethical concerns, ensuring fairness and transparency in automated trading. System integrity, protecting algorithms from manipulation and tampering. A unified approach to cross-disciplinary autonomics. Implementing autonomics across diverse sectors requires a unified framework that combines cross-disciplinary knowledge with scalable architectures. The integration of structure, coherence, and standardization ensures that autonomous systems maintain reliability and predictability, regardless of the application domain. Synergies between disciplines: healthcare and robotics, robotic surgery, driven by predictive analytics and sensor fusion. Energy and transportation, autonomous electric vehicles integrated with smart grid systems for optimal charging. Finance and data science, real-time risk management algorithms paired with autonomous trading systems. Manufacturing and cybersecurity, self-protecting smart factories that detect and respond to cyber intrusions. The future of autonomics, cross-disciplinary evolution. As autonomic systems continue to evolve, the interdisciplinary nature of their development will become even more pronounced. Collaboration between engineers, data scientists, ethicists, and industry specialists will be essential to maintain a balanced approach to innovation and safety. Emerging trends, integrated autonomics platforms, combining multiple disciplines within a single framework, adaptive ethical guidelines, developing cross-industry standards for safe and fair autonomy, predictive and prescriptive intelligence, moving beyond reactive systems to proactive decision-making autonomy. Conclusion: autonomics is not just a technological innovation, but a cross-disciplinary movement that reshapes how we think about automation and intelligence. By fostering collaboration and embracing holistic integration, we unlock the potential to create systems that are not only intelligent, but also ethical and resilient. Synergy of systems. Autonomics within broader frameworks. Autonomics does not exist in isolation. Instead, it operates within a vast network of interrelated systems, each governed by axiomatic fundamental truths that shape their functionality and purpose. These core truths are the foundation of axionomics, a paradigm that emphasizes the irrefutable principles guiding intelligent systems and their interactions. Axionomics represents a holistic approach to intelligent system design, rooted in the belief that every autonomous system must align with foundational truths that remain constant, regardless of context or application. This ensures that systems are not just intelligent, but also coherent, resilient, and purpose-driven. Autonomics aligns perfectly with the principles of axionomics, as both frameworks seek to establish order, consistency, and stability within dynamic environments. By embedding axiomatic truths at the core of autonomic systems, we ensure they remain predictable and reliable, even as they adapt to changing conditions. In this chapter, we will explore how autonomics fits within the broader framework of axionomics and how this alignment transforms intelligent system design and deployment. The essence of axionomics: axiomatic fundamental truths. Axionomics is founded on the concept that every system operates based on axiomatic principles, undeniable truths that form the backbone of rational and reliable operations. These truths are not subjective or situational, but rather universal constants that guide the behavior of autonomous systems. Core axiomatic principles of axionomics. Consistency. Systems must operate with logical consistency, ensuring that outcomes align with fundamental rules. Integrity. Data and operational processes must maintain structural integrity to preserve functionality. Adaptability. Systems must remain adaptive while maintaining core truths, enabling evolution without deviation from purpose. Transparency. Operations and decision-making processes should be traceable and understandable to maintain trust and accountability. Purpose-driven design. Autonomous systems must be built with clear, purpose-driven objectives, ensuring that their actions align with core truths. By embedding these axiomatic principles into autonomic systems, we establish a foundation of truth and reliability that transcends individual applications, making systems coherent and purposeful in diverse environments. The intersection of autonomics and axionomics. Autonomics leverages the core principles of axionomics to ensure that systems not only function autonomously, but do so with intrinsic purpose and consistency. This synergy results in systems that are not just self-governing, but also self-correcting and resilient, grounded in universal truths that guide their behavior. Key alignments between autonomics and axionomics. Autonomic self-governance as axiomatic truth. The ability of a system to self-regulate and self-govern is grounded in the truth that autonomy requires independence from external control. This aligns with axionomic consistency, where a system's decision-making process remains logically sound, even when environmental variables change. Structural integrity as a fundamental principle. Autonomics emphasizes robust structural design to maintain function despite disruptions. In axionomics, this equates to structural integrity, where systems are built on unbreakable frameworks that ensure operational continuity. Purpose-driven adaptation. Autonomics inherently adapts to new conditions, but without a guiding purpose. Adaptation becomes erratic. Axionomics embeds purpose as a core truth, ensuring that adaptation always aligns with fundamental objectives. Applications of axionomic principles within autonomics. 1. Smart infrastructure, maintaining consistency and integrity. Autonomics and axionomics converge significantly in smart infrastructure, where systems must operate autonomously while maintaining infrastructure integrity and purpose-driven efficiency. Key example, smart grids. Axiomatic truth, the grid must balance supply and demand consistently while integrating renewable energy sources. Autonomics implementation, self-governing nodes optimize energy distribution. Predictive maintenance systems proactively address equipment failures. Axionomic alignment. The grid adheres to the fundamental truth of energy conservation, maintaining balance through self-regulation and real-time adaptation. 1. Autonomous vehicles, truth in decision-making. In the realm of autonomous vehicles, truthful and consistent decision-making is essential for safety and reliability. Key example, collision avoidance systems. Axiomatic, truth, safety over speed. The system prioritizes human life above all else. Autonomics, implementation. Real-time sensor fusion and predictive pathfinding. adaptive algorithms that adjust based on road conditions and traffic dynamics. Axionomic alignment. Decisions align with the fundamental truth of protecting human life, maintaining transparent decision logic for accountability. 1. Data integrity in finance. Reliable autonomic systems. Financial markets demand consistent, transparent, and accurate data processing. Autonomics ensures that trading algorithms can self-adjust to market dynamics without losing data integrity. Key example: autonomous trading algorithms. Axiomatic truth. Maintain data integrity and accuracy to ensure fair trading practices. Autonomics. Implementation. Adaptive trading algorithms that analyze vast data sets in real time. Self-correcting mechanisms that identify and rectify data anomalies. Axionomic alignment. Ensures that trading strategies adhere to ethical standards, maintaining transparent auditing and accountability. Challenges and future directions. 1. Maintaining axiomatic integrity. One of the primary challenges is ensuring that autonomic systems consistently adhere to axiomatic truths, even as they evolve. Implementing dynamic truth-checking algorithms can help verify alignment with core principles. 2. Conflict resolution between autonomous systems. When multiple autonomic systems interact, conflicting axiomatic principles may arise. Developing meta-principles to resolve these conflicts while maintaining system coherence is crucial. 3. Ensuring transparency and accountability. Autonomic systems must maintain traceable decision logic, especially in critical applications. Building auditable frameworks that clearly document why and how decisions are made will reinforce trust and reliability. Conclusion: the synergy between autonomics and axionomics establishes a revolutionary framework for intelligent systems, one that transcends mere autonomy by embedding axiomatic truths as the foundation of operational logic. By ensuring consistency, integrity, and purpose-driven adaptation, autonomic systems become more than just self-governing technologies. They become pillars of intelligent ecosystems that harmonize with human values and societal needs. As we move forward, the intersection of autonomics and axionomics will shape how autonomous systems are designed, deployed, and managed, creating a future where self-governance and fundamental truths coexist seamlessly. Shaping tomorrow, the profound impact of autonomics. The rise of autonomics represents more than just technological progress. It signifies a paradigm shift in how intelligent systems interact with the world and with each other. From smart cities to healthcare, industrial automation to data-driven decision-making, autonomics is reshaping the fabric of modern society. Its profound impact is not limited to enhancing efficiency or productivity. It redefines autonomy, resilience, and adaptability at every level of human endeavor. This chapter explores the profound impact of autonomics, examining how its foundational principles and synergistic alignment with axionomics have fundamentally transformed various industries and social structures. We will analyze both the technological advancements and societal implications, shedding light on how autonomics is not just shaping the future, but creating entirely new possibilities. The evolution of human-machine interaction autonomics has revolutionized human-machine interaction, HMI, by enabling machines to learn, adapt, and respond autonomously. No longer constrained by rigid programming, modern autonomous systems exhibit contextual awareness and adaptive decision-making, drastically improving usability and efficiency. Key shifts in HMI, from command-driven to adaptive response. Early systems required direct human input to execute tasks. Autonomic systems interpret human intent and adjust actions accordingly. Seamless integration into daily life. Voice-activated assistants, smart homes, and intelligent vehicles. respond to nuanced commands. Machines now understand context and personal preferences, making interactions more natural and intuitive. Enhanced decision-making support. Autonomics assists humans in complex decision environments, such as medical diagnostics or financial trading. By leveraging machine learning and predictive analytics, systems can anticipate needs and recommend optimal solutions. Transforming industries with Autonomics. Autonomics has become a catalyst for innovation and transformation across numerous industries, fundamentally altering how processes are managed and decisions are made. Let's explore some of the most significant impacts. 1. Healthcare. Revolutionizing patient care. Autonomics in healthcare has moved beyond mere automation of tasks to creating intelligent systems that actively support patient care and clinical decision-making. Applications. Autonomous diagnostics. AI-driven systems that detect patterns in medical imaging and flag potential health issues. Smart monitoring devices. Continuous patient monitoring with real-time anomaly detection and predictive health analytics. Robotic surgery. Enhancing precision and minimizing risk through adaptive robotic systems. Impact. Reduced human error. Machines make fewer diagnostic mistakes, especially in image analysis and data interpretation. Proactive health management. Patients receive early warnings about potential health issues, improving outcomes and quality of care. Cost efficiency. Reducing the burden on healthcare providers by automating routine and repetitive tasks. 1. Manufacturing. The rise of the autonomous factory Autonomics has revolutionized manufacturing by enabling smart factories that self-regulate and self-optimize without human intervention. Applications. Predictive maintenance. Machines anticipate and resolve issues before they cause downtime. Adaptive production lines. Systems dynamically adjust speed and configuration based on real-time demand. Automated quality control. Vision systems detect defects with unprecedented accuracy. Impact. Enhanced productivity. Minimizes downtime and maximizes output. Precision and quality. Automated quality assurance reduces human errors and inconsistencies. Scalability. Production systems can easily adapt to new product requirements or market changes. 1. Energy and utilities. Smart and resilient grids. The energy sector has embraced Autonomics to create smart grids that dynamically balance supply and demand, integrating renewable sources and enhancing grid resilience. Applications. Demand response systems. Automatically adjust energy distribution based on real-time consumption data. Self-healing grids. Detect and isolate faults, rerouting power to maintain continuity. Renewable integration. Smoothly incorporates solar, wind, and other variable sources. Impact. Sustainability. Reduces carbon footprints by optimizing energy use and minimizing waste. Operational continuity. Maintains uninterrupted service during disruptions. Cost reduction. Lowers operational expenses by streamlining grid management. 1. Transportation. Autonomous mobility and traffic control. Transportation systems are being transformed through Autonomics, making mobility safer, more efficient, and more environmentally friendly. Applications. Autonomous vehicles, AVs. Self-driving cars that navigate and adapt to road conditions. Smart traffic management. Synchronizing traffic signals to reduce congestion and emissions. Fleet optimization. Real-time tracking and routing adjustments for logistics. Impact. Safety and reliability. Reduces human errors and accidents. Traffic efficiency. Minimizes travel time and fuel consumption. Logistics. Innovation. Increases the reliability of delivery networks. Societal implications of Autonomics. While the practical benefits are vast, the rise of Autonomics also raises profound societal questions. From ethical concerns to workforce displacement, understanding and managing the broader impacts of autonomy is crucial. 1. Ethical and moral considerations. Decision accountability. determining who is responsible when autonomous systems make mistakes, bias and fairness, ensuring AI-driven decisions do not perpetuate or exacerbate biases, privacy concerns, managing sensitive data collected by autonomous systems. 1. Employment and workforce transformation, job displacement. Automation in industries like manufacturing and logistics may reduce the need for human labor. Skill evolution. Workers will need to transition from manual roles to supervisory and analytical positions. Economic shifts. Entire business models may evolve to integrate autonomics-driven efficiencies. 1. Social equity access. Disparities. Ensuring that advanced autonomic technologies are available to diverse populations. Digital divide. Addressing inequalities in technology adoption and infrastructure. A glimpse into the future beyond automation. The future of autonomics lies not just in enhancing efficiency, but in transforming societal structures. As systems become more intelligent and interconnected, autonomics will foster adaptive ecosystems that are self-sustaining and resilient. Key future trends: holistic ecosystems, integrating autonomics with circular economy principles to promote sustainability and resource efficiency. Human autonomous collaboration, merging human intuition with machine precision to enhance problem solving. Policy and regulation, crafting adaptive governance frameworks to manage the societal impact of pervasive autonomic systems. Conclusion. The impact of autonomics transcends technology, touching every aspect of modern life and future innovation. By enabling systems to think, adapt, and act independently, we are crafting a world where machines augment human capability rather than simply replacing it. However, this transformation demands a careful balance of technological advancement and ethical considerations, ensuring that progress benefits all of society.